Hey everyone, welcome to another edition of Ask an Astronomer. My name's Michael. I am here in our Ground Station Canada Theatre at the H.R. MacMillan Space Centre, located on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh. And because this is Ask an Astronomer, we are here with my, your astronomer, Rachel Wang, who is not upstairs. She is somewhere very interesting. It looks like a honeycomb. Looks like you're with a lot of flowers. We're going to learn about. You're not actually there, but you have a special background, Rachel. You're going to explain where you are, right?
Sure. Yes, I wish I was there. That'd be cool, but no, unfortunately not.
So, Rachel, this week we've got lots of really exciting news to get to. Of course, our favorite red planet, Mars, our robots, lots of activity going on there. So, we've got an Ingenuity update, some Perseverance, and of course, what's going on behind you, plus a bonus news item as well. But we'll save that bonus news item. But, Rachel, why don't you start us off with the big news of this week? And, of course, welcome to all of you that are watching on YouTube. If you want to join in on the conversation, we'll be going till 2:30 p.m. Pacific time. Put your comments into the chat window. We will get to all of your questions. And at the end, I'll also let you know about all of the events we got coming up. But Rachel, take it away with our first big news story of the day.
Like, sure thing. Alrighty, so the theme today is liftoff for, first of all, for Ingenuity. And NASA is targeting no earlier than Sunday, April 11th for Ingenuity's first attempt at a powered, controlled flight on a whole other planet. And so the live stream that's going to be streaming this first attempt is targeted to begin around 12:30 a.m. I don't know about you, Michael, that's way past my bedtime, but I will get up for this one to watch this because
It's right around my bedtime.
oh
So,
yeah,
maybe I'll stay up. But it's Monday, though. So we'll see.
it's an important moment because it
Yeah.
is a historical moment because it's kind of like the Wright brothers when they had their flyer, except that it's a further distance, they're flying for a longer duration, and it's on a different planet. So kind of a big news there. So for everyone watching, I'm really encouraging you to go and watch this event when it happens, hopefully on Monday, and the link that I put there is where you can find it. And of course, keep in mind that this flight date may shift depending on the engineers when they're working on deployments, things like pre-flight checks, all of that can shift the date a little bit as well. But you can find the schedule on that link as well.
And I'm also, once we're done here, I'm going to put this link into the notes on this YouTube. So then you just click it and set a reminder for yourself 12:30 a.m. Pacific time.
Perfect. All right, so this is Ingenuity. It arrived at Jezero Crater on February 18th,
Oh,
and
cute.
it was carried along as a stowaway or passenger underneath Perseverance. And this is a real picture. It's not an artist rendition. It's a real picture taken by the mass cam that is on Perseverance. And those are a pair of two zoomable cameras on the rover. This was taken on Sol 45, which is the 45th Martian day or the 45th day of the mission. So for the flight, the helicopter will have 30 sols, or 30 Martian days, which translates to 31 Earth days, to conduct what hopefully will be a series of test flights. And deploying the helicopter itself is going to take 6 sols, so they have to factor that in as well. And so they have a limited time window to do all of this, because once things get set into motion, all the tasks that Ingenuity has to do are closely coordinated, they're irreversible, and they're all dependent on one another, so they have to be extra careful not to damage the helicopter. And the site that they chose for the airfield is a 10 by 10 meter site, and they chose it because it's relatively flat and there aren't a lot of obstructions in the way. So you might have seen this slide before, but this is showing you where Perseverance is going to be in relation to the airfield. So down on the bottom, you see the Van Zyl overlook, which is where Perseverance will be parked, and it'll watch Ingenuity's attempt, and that will be on the right-hand side what you'll see as Perseverance if you're watching Perseverance do its flight. And so the rover is there because it's going to provide support during flight operations. It's going to take images, collect environmental data, and also host the base station for communications relay between Ingenuity and also mission control on Earth. So what is Ingenuity doing? Well, this is an image showing what one test flight might look like. And we're hoping that this is the live stream that we'll be seeing this flight path. And also, I think they're also going to analyze the data as well at JPL on that live stream. So that's really cool, getting the data and seeing how they interpret it.
Awesome.
Mhm. Other milestones from Ingenuity include it survived its first Martian really, really cold night on its own. And at Jezero crater where it lives, temperatures can drop as low as 90 degrees, negative 90 degrees Celsius, which is really, really cold. And that also means that it can freeze and crack anything that's unprotected, like electrical components and damage onboard batteries that are needed for flight. So a lot of things could go wrong in very, very freezing temperatures, but Ingenuity survived day one.
I
And
love how
this,
that's like at the top of the priority. Like, step one, just
yeah,
survive.
just make it through the night. That's all we want. But this is the first time that it was on the surface of Mars all by itself. And because it survived, that tells us that it has the right heaters, it has enough energy stored in its battery to withstand that frigid Martian temperature. And the right-hand side is an image taken by Ingenuity with its color camera from beneath Perseverance. You can see Perseverance's wheel in the top left-hand corner. And this is the same camera that we're hoping that Ingenuity will use to take higher resolution images as it's going along each of its tests. So each test should have a high resolution image attached to it as well. And yesterday, the restraints on the rotor blades have been unleashed, I suppose. And and the next several sols will involve a lot more testing of the rotor blades as well as the motors that drive them. So you can see that in this checklist, we're actually pretty close to the end. We're pretty close to actually firing up the blades and lifting off for the first time and hopefully landing successfully.
Awesome.
Alrighty.
One question I have, Rachel, before we move
Sure.
on, and if anyone out there has any questions about Mars and Ingenuity. So, you mentioned that the Sol days. So that is, of course, the days that Ingenuity, Perseverance have been on Mars, correct?
Mhm. Yes.
And every mission has their own timeline. So Curiosity would be on a different Sol, and let's say Opportunity would be on a different Sol. Is that also correct?
Exactly, yeah, and that's the reason why we use Sol instead of Earth days, because time is, or I guess days on Mars are a little bit different. Days on Mars are, I think, 40 minutes longer, about 40 minutes longer than one day here on Earth.
Okay. And so when those teams are working together, and of course, some of those images that you just showed were from the Mars Reconnaissance Orbiter, um, would they also be on their different timelines? And when they're like collaborating with each other, even as we are over Zoom, if we're talking to someone in a different time zone, we kind of have to match up our timelines. So when they're talking to each other, is there some collaboration that has to happen just to get their times right?
Are you asking about the individual spacecraft or like international collaboration with space
Well,
agencies?
I suppose like it's for the different teams. So I'm not just talking about,
Yeah.
on Earth, but for the team that's working on Sol 300 whatever with
Mhm.
Curiosity and Perseverance.
Sure, yeah. So they would all follow a very similar timeline. So they wouldn't say that Sol 1 is a different day. But relative to each mission, they count how many sols has passed for that particular mission. But you can place it on a timeline which Sol since the first robot landed on Mars.
Right. I wonder if there'll ever be a point when there's just so many missions on Mars that they have to also come up with like an actual official Mars time, and that everyone has to use so that they can all be on the same page.
Because we have a universal coordinated time here on Earth, so
Yeah.
we can't say that it's universal anymore if you're going to do it on Mars as well.
Awesome. Well, super excited about that. You know what? I think I am going to stay up for that on Monday night. It's not too late. I can do it. But we also have some more news about that big honeycomb behind you. So let's get to our news story number two.
We sure do. And Michael, you know how much I like to talk about James Webb, so I had to share the update that came out yesterday. And so what happened was the engineers that were working on the James Webb Space Telescope, or JWST, they successfully folded and packed the telescope's sun shield away for its 1.5 million kilometer journey later this year on Halloween. And it might not sound super exciting, but it is, because this is one step closer to James Webb actually going up into space. They've actually packed their bags and stowed some of the things in the trunk of the car, and they're getting ready to drive it, getting ready on Halloween to launch it into space. So I'm a little bit optimistic because of that. Now, this is the sun shield. So this is the thing that they packed away. It's the largest part of the observatory, and it consists of 5 really thin silvery membrane layers that are roughly the size of a tennis court. And each layer is very, very thin. It's about as thin as human hair, or like 1/1000th of an inch. And they're made of a material called captain, which is a plastic that's commonly used in cryogenics because it's very stable over a wide range of temperatures, and it's also very, very strong and light.
Cool.
So the question is, well, why did they make 5 layers? Why didn't they just make one super layer and make it very, very thick? And the answer to that is because the layers are separated by vacuum, and vacuum is a really good insulator because we know that vacuum lacks atoms, and so it's often used to reduce heat transfer through processes like conduction or convection. And we use this to our advantage in many different ways. Like Michael, I don't know if you have a tumbler or a thermos, but I do, and it has a vacuum inside to act as an insulator to keep it either very hot or very cold. But
Which is why when I pour my coffee out into like a normal mug, it like gets cold like within like 5 minutes, and I'm always having to go back and reheat it. It's very frustrating.
exactly, you need vacuum insulation. That's what you need. But objects can still emit radiation to cool down. So in the sunshield, heat radiates from between the layers, meaning that each successive layer of the sunshield is cooler than the one before. And if it was just one super thick layer, then the sunshield would conduct more heat from the bottom to the top rather than having that successive cooling down. Now, folding the sunshield isn't as simple as it might sound. It's a very, very delicate process, and it lasts for about a month. And not only are the layers super thin, but they had to be really careful with the 90 different cables that provide tension to the layers that are also stowed away in a very specific way with the sun shield. And the technicians, to fold it, they made it in a zigzag pattern to create kind of like an accordion of stacks of membranes. And Michael, yesterday I went and made a little accordion myself using 2 sheets of paper. That's basically what they did. They folded it really nicely and put it on either side of the telescope. And that's what these arrows are pointing at here.
Oh, that's awesome.
So the intricate process of folding these membranes and aligning them is the fact that these sun shields have a bunch of holes. And these are intentional holes. These aren't just holes that came out from production. And these holes are wanted because they can be arranged in such a way that it avoids blocking light reaching those optical elements that are very sensitive. And when we fold the sun shield, we want to make sure that those holes are lined up so that the technicians can insert pins through the holes through each membrane in the stack. And there are 107 of these pins, or what they call membrane release devices, but I suppose pins is a lot easier to remember. And this will secure the layers for launch, but they'll release and unfold the shield once it's in space. So they really want them to be aligned while they're folding, but they want them misaligned when they're up in space so they do provide that full coverage.
I love that picture of that engineer because you look and he looks very COVID safe, but this is actually how they always look, even if we weren't in the middle of a pandemic, because they're also protecting the spacecraft from our germs, right?
For sure, yeah. They describe it as having a clean room inside of a clean room just to make sure you're extra clean.
Amazing.
All right, so since JWST and specifically the sun shield is so large, it has to be very carefully folded around those gold mirrors and instruments during its ride on the Ariane 5 rocket. And once it reaches orbit, it'll unfold and separate into the 5 layers and looks a lot like a kite does. And so you can think of the sun shield as kind of like a beach umbrella. It can be folded into a smaller size, and when you deploy the umbrella, it keeps the shaded area cooler, and it also lets you stop squinting as much in bright sunlight. And that's pretty much what the sun shield is going to be doing. And these images on the left show how the telescope will fit inside the rocket. And they chose this type of rocket because it's known for its heavy lifting capabilities, and JWST is not light. It weighs about 6,500 kilograms or 14,000 pounds here on Earth. So they really did need a heavy duty thing to launch something that is about the size or heaviness of a full-sized school bus. And it weighs just a little bit more than half the mass of Hubble. So Hubble was also very, very heavy.
Nice.
So the shield splits the observatory into 2 sides. There's the warm sun-facing side, which will be on the bottom here. And on the side, temperatures reach roughly 110 degrees Celsius, or even somewhere between 80 and 120. there. And then on the opposite side, where we're having all these sensitive instruments on top, that is the cold side. It drops to about 36 Kelvin, which is negative 237 degrees Celsius. And this is where the sun is blocked from interfering with those infrared instruments. And the telescope itself is operating under 50 Kelvin. Now, there is a specific reason why James Webb is operating at such a low temperature. And it's because JWST is observing primarily in the infrared, which is colloquially referred to as heat. And there's a difference between heat and infrared. Infrared is the infrared part of the electromagnetic spectrum. Heat just generates light in that part of the spectrum. So it's a little bit different. You can think of it as heat energy, and then infrared as just something on a scale. But in order to detect ultrafaint signals that are coming from really far away objects, the telescope has to be very, very sensitive and also very, very cold. And because it's detecting infrared light, it has to shield itself from external sources of light and heat. Now, I mentioned the sun being a really big contributor to that light and heat, but also the internal instruments themselves, as they're operating, also emit heat. So if they didn't keep JWST cold, then the sensors and the detectors would be blinded by their own infrared emission. So it's really important that they're kept quite cold.
It's really cool, this image here that you have here showing this different size of the Hubble and JBST, like a much larger primary mirror than Hubble has. But you even included a sort of scale there, and I was going to ask, if you had actual measurements, but I can actually probably see, because even today we are using our telescope. We are looking at the sun actually today, because the sun is out here in Vancouver. So I would say that our telescope is about half, maybe even less than half, a little bit less than half of the size of Hubble's primary mirror, which is really, really cool. So that's, for anyone out there living close in Vancouver, if you get down here, before 4 o'clock, you can get a ticket. You can look at the sun. We're looking at the sun with our telescope as well. But a good question, Rachel, which I don't know if it's going to be the next part, and if it is great, we can transition into what JWST is going to help look at out there in the universe that Hubble can't.
Sure. So it isn't the next slide, but I'm happy that you brought that up, because they did actually they decided what the primary science objectives, specifically each program, will be. I think earlier in the week, I want to say even just 2 days ago, they figured out and pinpointed exactly what they wanted to look at. But the overall science objectives they had from the start, and that is that the primary aim for JWST is to look at the first light in the universe. And that's much, much further, much further in time and distance than Hubble can see. And that's partly because, or mostly because, of the fact that it's looking at infrared light, whereas Hubble was looking at the visible spectrum. And it's looking for objects that formed very shortly after the Big Bang. So it's looking at things like, or how objects evolve. So things like how galaxies form and evolve, things like studying the birth of planets and stars, looking at our own solar system and our own evolution, and studying the properties of exoplanets, because in the infrared you have a lot of nice signatures in exoplanet atmospheres, and they just happen to peak in the infrared. So there's a lot going on for JWST here.
Awesome.
And actually, just before I move on, I'm going to point out the bottom picture here, Michael, that you were talking about before. And then you'll notice that there is a circle going around the primary mirror. And you'll notice that Hubble is also a circle. So that's part of the reason why they chose hexagons, because it saves a lot of space. If they had circular mirrors, then you have a lot of gaps in between. So the hexagon shape minimizes the amount of gaps between everything. And they want it to be circular because then it focuses the light in the center. If it was something like an oval mirror, then you'd have the image elongated in one way. If it was like, let's say, maybe a square mirror, then you wouldn't have all the light focused in the center, and you'd lose some of the light on the outside.
And it's just an efficient shape as well. Like we're literally borrowing from bees, because bees, they're workers, and they need to be efficient as well. Maybe they're not thinking about being efficient, but they've evolved, to be efficient, and that's pretty cool that we are using nature as inspiration.
Yes, which is why we should save the bees, because we get all of our inspiration from them.
Absolutely. Well, for more reasons than that.
Sure, sure. But moving on, I just decided to include a lot of really cool images of JWST, because they have a very nice gallery as they're going through their progress and building JWST. So this is specifically about the sun shield. And you'll notice that in some of the pictures, the shield is a little bit curved. So that also adds to the difficulty of trying to stack those layers together. And down here is the NASA administrator, Charles Bolden. He was a NASA administrator from 2009 to 2017. And then on the right-hand side here, they're testing a little piece of the sun shield in a vacuum chamber to see how it'll do in space.
Cool.
And so here are more images of the primary mirror, where you see on the top here, there is this black structure. And what this is called the JWST Pathfinder. Now, this Pathfinder won't be part of the actual thing that's going up into space, so we call it a non-flight object. And it's really just to act as a prototype to make sure that when we build the actual thing, we're not wasting more billions of dollars that we already have in the progress of making and planning JWST. And you'll also notice that there are two different colors here on the mirrors, but the full one behind me is all gold. So it is gold on the surface, it's a very thin layer, but underneath it's mostly made out of beryllium. And it's made out of beryllium because it's known for its high strength to weight ratio, and it's good at holding its shape at very extreme temperatures. But beryllium is also, interesting enough, I didn't know this before, but it's a rare metal and it's mined and processed in only one place in the Western Hemisphere. And so they've, I guess, funneled all of it into JWST. And that's it.
Awesome. Well, Rachel, we only have about 8 more minutes. We've got a few questions that we're going to get to. But before we get to that, I do want to have time for another big announcement that you have some personal news that you'd like to share.
Yeah, so I'm going to be learning more. So this is my last Q&A Ask an Astronomer with you, Michael, which I am very sad to leave because I love it when people ask me questions and talk about space, and so I don't bug my roommates about it. But yeah, so I'm going back to school. My reason for that is that I love math too much.
Well, that's a good. Is that really like your primary reason you love math so much that you're going back to school to learn more?
You know, I do miss math a lot because when we make presentations, I try to limit it to only one equation per presentation,
Yeah.
which it's hard for me to choose a good equation for whatever topic it is, because I want to throw so many up there. So I'm going to go back to school and satisfy that craving.
Well, this is amazing news for you. I mean, really sad for us. So you're just going back for math. Or what specifically are you going to be studying when you go back to UBC?
A master's in physics.
Oh, okay,
Yeah.
nice.
Yeah.
Well, Rachel, you've been with us for almost a full 2 years. I remember when you first came on, I was going to Banff for a science communication course, and it was around the time sort of like transition, and it just happened to be the 50th anniversary of Apollo, and that was a bit stressful because I usually don't take vacation, but I was like, you know what, I'm going on vacation. We've got a new astronomer. She'll do great. And I remember being in Banff and watching all of the clips of you, like in your first week on TV. We just thrust you into the spotlight, and you did amazing. And I knew right away that you were going to be a great partner with us, a great advocate. Rachel, I'm so proud of our time together, and I'm really sad to see you leave. I'm so proud of you. I hope you stay in touch. Maybe even join us randomly for some Ask Astronomers, or maybe even we'll bring you in as a special guest someday.
That'd be really nice. Yeah, maybe I'll come back for cosmic nights.
We've got so many messages coming in on the YouTube for you, Rachel. You're going to have to read them later. But I also want to introduce because Rachel's leaving, which means we get to introduce our new astronomer. So I'd like to introduce to you all to Marley Leacock, who also is from the University of British Columbia. But currently, Marley is in Calgary, where it's not as sunny as it is here in Vancouver, but Marley soon will be traveling over to Vancouver and joining us. How's it going, Marley?
It's going well. Wish it were sunnier, but I'll take what I can get. It finally stopped snowing, so that's nice.
Well, Marley, excited to have you join the team. Excited to have you start to join our Ask Astronomers. Why don't you tell us a little bit about your background? Like, what would you really focus on when you were in school?
Yeah, so when I was in school, I tried to do a little bit of everything, but I found myself particularly drawn to galaxies and galactic formation and galactic lifetimes and things like that. And so I actually ended up doing a research project at the University of Toronto all about these special types of galaxies, active galactic nuclei. So these galaxies that have really, really active centers for whatever reason, and identifying different candidates in a certain region of the sky of galaxies that could have those characteristics.
So your astronomy superpower is galaxies. Is that what you're saying?
Well, would I call it a superpower? I don't know, but it's definitely, if I had to pick a favorite, I'd err on the side of galaxies.
Rachel, what's your astronomy superpower?
Ooh.
I guess
Any object that's far away. Like
I guess when I say
very far away.
superpower, I mean like house. I mean like if we're like going into like the Hogwarts sorting house, like which astronomy sorting house would we put you in?
Ooh. I'd probably say clusters, globular
Okay.
clusters. Yeah, groups of galaxies. So I guess I'm in the same camp. Galaxies.
Yeah, I'm probably more of like a planetary science guy. That seemed to be always what I gravitated towards, but maybe that's because like all the stuff that you guys are studying now, I don't even think we could study back when I was going to school. Like it wasn't even, we made so many new discoveries that largely has to do with Hubble as well, because when I was going to school, Hubble was not even on the radar yet. So Hubble has really opened up our field, and now this is really exciting for all of the people watching. All of the new fields of discovery and science that James Webb is going to open up. This is a really exciting time to be in astronomy right now.
Michael, I'll add that in 1929 is when Edwin Hubble announced his discovery. So I don't know if that dates you at all, but I wanted to throw that out to the audience.
Well, the audience can they can do the math, and you can figure that out. Wow, I can't even go through some of these comments. So many coming in. There was a question before we dropped the big news about building James WST. Of course, could you maybe talk a little bit about how they built it? Of course, like that's a big topic, and there's lots of different parts to it. But maybe just sort of like in general, some of the specifics of how they built it.
Sure. I'm actually going to pull up another slide because I prepared for this to talk about NASA's budget and schedule for James Webb, because I have a little bit of a gripe with them about that. So you can see this. So can you see the budget and schedule from 1997 to 2020?
Yep.
Great. So we give NASA some allowances because they did go through a major redesign in 2005. So I'd rather them get it right than rush the project. And when they finally completed construction, that was in 2016. And then from then, they started doing a lot of tests. So things like cryogenics tests to make sure that it will survive the cold night, just like Ingenuity has. And things like stress tests and deployment, all those kinds of things. And they did actually accidentally rip one of the sun shield layers during deployment, so they also got delayed by that. But James Webb has all of its components built at, I believe it's JPL, but they also outsource some of the construction to other places like universities. I believe the University of Arizona is a major player as well. And yeah, I don't really know what else to say besides that they're very slow, but I hope that they'll finish and launch by Halloween.
Do you think that as you go through your master's, Rachel, that you're going to maybe get on a project, maybe to work with some JWST data?
I hope so, because when I was in school for my undergrad, I remember having the announcement in class about the gravitational wave detection. So I'm hoping that the same kind of thing will happen with JWST, where I get to share with all my classmates the excitement of something new happening in space.
Marley, if we were to give you some time with a JWST, what would be something that would fill your fancy about the cosmos?
Well, I think what Rachel mentioned earlier about looking back at like the first light of the universe, I think is the coolest thing to possibly look at. So I'm already pretty excited for that part, if and when this telescope finally gets up and running.
Absolutely. And, October 31st, we've got that date circled. And Marley, I can certainly see us probably doing an event around that time. So start preparing for that. And hopefully maybe we even can do something in person as well as we start to open up more. So we got lots of exciting possibilities. We're at our time, 2:30. Rachel, this is our last Ask an Astronomer. Any last words for your last show?
No, but I wanted to thank the audience for having a lot of good questions and being very engaging and listen to me ramble about space for so long, and I really appreciate that. So thanks for having me.
Awesome. Rachel, all the best to you. All of you watching out in YouTube, thanks for joining us. We will be back in 2 weeks with Marley, our new astronomer. In 2 weeks, it's Earth Day. So we are going to have a special guest from the Canadian Space Agency, Taryn Tomlinson, who's going to be talking about Earth observation satellites. So make sure to join us in 2 weeks for that. Plus, like I mentioned before, our telescope is open right now. We're looking at the sun. We are open Thursday to Monday for in-person visits. You can go onto our website, spacecenter.ca, and book your visit. And we also have some special events. Rachel does have one more event, even though it's not, we don't have another Ask an Astronomer. On April 14th, Cosmic Nights is going to be her last official day and her last official event. We are going to be talking with Stuart Bartlett from Caltech on the big question of what is life? This is going to be a big one. This is a really exciting one. I've been wanting to do this for so long. We're going to be getting into of the astrobiology, lots of big questions all around that big theme. I even have a special interview that I'm going to be talking with tomorrow, actually, Sarah Seeger from MIT, who is studying exoplanet atmospheres. Just an amazing scientist who's actually a Canadian working down in MIT. So that's going to be a bonus interview. Exclusive for people. They get tickets for the Cosmic Night on April 14th, so you don't want to miss out. Once again, you can get those tickets on our website, spacecenter.ca. And that's all for me. Thank you so much for joining us. Rachel, all the best.
Thanks.
Ad Astra.
Bye.